Hey everyone, can you hear me? Am I good? Can you see me? Just type a yes in the chat just to make sure I'm good and ready. Um, Welcome everyone, and thank you so much for joining one more time. Can everyone see or hear me? All good? We'll get started in a couple more minutes, waiting for some more people to join in. But in the meantime, feel free to, if you feel comfortable, introduce yourself on a message in the chat. Feel free to type your name, your organization, the country you're calling in from, and then the environmental issue that you're most passionate about solving in your community or your country. Thank you. Thank you all for confirming. We are good. So, yes, go ahead and introduce yourself so you can probably connect with each other. I'll talk more about that towards the end on how you can effectively connect. But in the meantime, in the next couple minutes, if you feel comfortable, go ahead and introduce yourself. It'll be nice to see more intros. All right. One more minute, and then I'll wait for at least one intro. I'm monitoring the chat on my phone, um, but let me know if you have any issues or access issues. I see some familiar names. Welcome all. Thank you so much for joining. All right, we got Angela. Thank you for introducing yourself. Michigan Tech University. Welcome. I'll wait one more minute until we start. Al Noor from Atlanta. Welcome. Okay, methane emissions increasing. That's great. Um, I'll actually mention a project that we are almost finalizing regarding that. Awesome. So we'll just get started with this session. We'll have a short break in the middle because it is estimated to be 2 hours, but you'll find that this is a very much an information dense webinar, and feel free to take notes if you like to, but you can come back to this and watch it and take notes. So I'd rather you watch this than take notes and miss out on anything. But there'll be a lot of resources, a lot of examples, and you'll see clearly how geospatial data can be used for specific climate actions. So with that, let's start off with this intro to geospatial data science for climate action. This will be split into a basic intro to remote sensing, which is going to be quick, and then many, many examples along the way, and after that on specific climate action use cases. So a little bit about me. You may already know this, but just to give you a background of where I'm coming from, currently I'm the executive director and founder of a company called PlanetSapling. That's the YouTube channel name, that's my Instagram name. PlanetSapling, and basically we leverage satellite and sensor data to map climate and biodiversity risks for climate change mitigation, adaptation, and conservation. I'm working with several clients at the moment, focusing on certain climate adaptation data products development. So things like wildfire risk. National Parks is hiring for a vegetation mapping inventory project. So things like that, and I'm continuously working and finding opportunities to insert data into action-oriented use cases. I'm also the director of operations of a nonprofit based in Huntsville, Alabama. That's where I'm located. It's called Mycelium, and Mycelium is a nonprofit focused on accelerating the circular economy through open source solutions for waste management, food resilience, and self-sufficient housing. An example project that we've done is create an AI model that can detect and identify different types of recyclable waste, like PET type 1 plastic, HDPE or milk jugs, aluminum cans, cardboard, and glass. And we also created our own data set using trash we picked up from recycled bins from our neighbors. So that's the kind of projects we do using small grants. And then my previous work experience, my first job really, was at a partnership between NASA's Earth Science Division and the University of Alabama in Huntsville, where I studied. And that's called Impact, NASA Impact. And I was a research associate for nearly over a year and a half, and I conducted projects on detecting floating marine debris, identifying aircraft contrails on satellite imagery, and my background overall is in earth science and physics, and currently I'm also doing a part-time graduate degree program at the Arizona State University, focused on biomimicry, which is how do we apply and learn from different species, ecosystems, nature, to solve human challenges, because nature, as you know, has evolved for 3.8 billion years, much longer than we have, and many species have the solutions to problems that we face now. So that's what I'm up to. And my story, really, my passion for environmental issues began in my life in Mumbai. So I grew up in the city of Mumbai in India for 10 years, and I really wish these were AI generated images, but these are real images of plastic pollution, sewage pollution, landfills, open landfills in the city of Bombay. And this is a common sight across many countries that I visited in the developing world. And seeing this on a day-to-day basis really ignited my passion for finding solutions in a way that we live. And I really believe that we don't have to live in a way that harms nature or our surrounding environment and other species. We can find ways to do the opposite and actually be stewards of our lands. So with that, after my life in Mumbai, I went to school here. I did my bachelor's degree here, and started hiking, finding what local species exist around me. The first image is a chicken of the woods mushroom. I also was president and vice president of the Green Club, which is a sustainability student-led club in the University of Alabama in Huntsville, and volunteered a bunch. That's a picture of me in a beach cleanup in Mumbai during a summer break. And the last image on the right is me sitting next to a statue of Rachel Carson, who you might know as the author who wrote The Silent Spring. And that is one of the most powerful books that really led a revolution on banning DDT and then creating awareness on how pesticides harm ecosystems and then ultimately us. So that's a little bit about me. And then this is just a quick rundown of my GIS-based experience. My first GIS experience was at NASA Develop. That was a student summer internship, or actually fall internship in 2016. And I was part of a team that was monitoring water hyacinth, that's an invasive species in Lake Victoria. In 2017, during the summer, I did a 1-month immersion in the Amazon rainforest. And that was one of the most life-changing experiences I've had to date. In 2019, I finished my degrees in physics and earth system science. 2020, like I mentioned, I joined NASA Impact. 2021, developed a data set and model that detects coastal marine debris. And this is part of feature detection that I'll briefly mention later on. 2022, I joined a climate tech startup called Climate Engine, and I focused on developing climate hazard data sets. So things like extreme heat, wildfire risk, drought risk, extreme cold, all these kinds of products I helped develop and co-led those things. And then in between 2022 and 2024, I worked on all the work at Climate Engine. And in August this year, I started my company PlanetSapling that focuses on geospatial data and media services for adaptation, mitigation, and conservation. So I'm involved in the Huntsville Sustainability Commission, also helping to create a documentary series called From Soil to Soul, focused on food justice and food sovereignty. And my passion is really disseminating information in a useful manner that can lead to climate action. Okay, so with that quick intro, let's move forward. So climate solutions, I just wanted to start off with this instead of geospatial data, because we have two really great frameworks of climate solutions that exist today. And the first one you might have heard is Project Drawdown. It's a set of climate solutions ranked by emissions reduced and then economic cost of implementation. So I already have Drawdown pulled up. And in their table of solutions, basically they're ranked by scenarios, what CO2 emission scenarios, and then you can click on any of these. For example, let's click on coastal wetland restoration, and you'll find a page that tells you about the impact of restoring wetlands globally. It tells you a little bit about what you can do. If you live near a coast, write a letter, volunteer, expand your knowledge. And then it tells you about the methodology that they created for finding the impact of coastal wetland restoration. So every single page has this kind of format where they tell you a little bit about what you can do, but mostly about the methodology they've used. So that's Project Drawdown, and I'll tell you why that I'm doing this in a little bit. So bear with me. By the way, this image is refrigerators, because alternative refrigerants are one of the top climate solutions that Project Drawdown identified for climate mitigation, because HFCs that replaced CFCs are really high. They have a really high global warming potential, so they trap a lot more heat than other gases. So the other most important framework, I'd argue, is Project Regeneration. And what they have is they've built a nexus of climate solutions, much like Drawdown has. But the difference is that within each of these nexus solutions, for example, if I let's click on palm oil, because I have something to show later. If I click on palm oil, they have, the definition of what it means and why it is a climate issue. And it's palm oil plantations are replacing a lot of tropical lands, especially in Southeast Asia, parts of Africa, and even South America, and Ecuador and Peru. And this obviously leads to biodiversity loss, but also a lot of emissions, because these are susceptible to wildfires. So what happens is that in the Project Regeneration page, they have action items for individuals, very specific action items that you can follow or conduct. They have action items for groups, as if you are part of a palm oil growing group, or the manufacturing industry, or if you know someone in the food industry which uses or sources palm oil, these actions are for them. And then companies, as in what can companies do to prevent using bad palm oil from sensitive regions. And then this is a good list of bad actors. They also have the CEO's names, emails, phone number, which is wild, but necessary in this case. And then key players. So which key players are involved in helping transition to sustainable palm oil practices. And then individuals who are spearheading such efforts. And then they have learning resources, which are documentaries, articles, and books. And sometimes they have listening podcasts. So this is the format for every single one of these solutions, and I'll let you explore it in your free time. But the reason I'm showing you these frameworks is because what I want you to do throughout this call and even after is try to link which solutions within Drawdown and Regeneration can use geospatial data for effective implementation. That's the key. We are trying to link existing climate solutions with existing geospatial data sets and practices, or things we can do with satellite data as data practitioners. So with that, let's get started with geospatial data. Obviously, it is information linked to a specific location on the Earth in this case. There can be planetary geospatial data as well for exoplanets, but we're just talking about the Earth in this case. And usually you have a base map, then you have satellite imagery, then you usually add on land cover, and then you can layer and make it as complicated as you want. You can add demographic data, in this case, wetlands, topography, zoning, whatever you want. You can add layers on layers to analyze, and we'll talk about what kinds of data sets you have. But there's so many satellites now. I think the number is now over 12 to 1,400 Earth observation, not total, but just Earth observing satellites. Usually from the European Space Agency, from NASA, from the Chinese Space Agency. India has its own as well. So, and so does Japan. So a lot of countries have their own satellite constellations, But now there are many private companies, as you know, Planet, Maxar, that have their own satellites too, and it's leading to some space debris ultimately. But I think this is an advantage for us to use so much data for good. And satellite data is still very heavily underutilized compared to what it can be. So, what are the types of geospatial data? Two major types is raster and vector. These are like the broader categories of geospatial data. And raster represents the world as a grid of equally sized cells or pixels, and each cell has a value, representing something like elevation, temperature, whatever it is. And it's best suited for continuous data, like satellite imagery, elevation models, temperature grids, precipitation grids. And generally, the format of raster data are GeoTIFFs, NetCDFs, HDFs. Generally speaking, those are the major categories of raster data. Now, vector data is spatial features like points, lines, polygons. These are discrete, not continuous. And points define specific locations like cities. Lines can define roads, rivers. Polygons can define land parcels, mines, lakes. And these are best suited for things like road networks, property boundaries, landmarks. And generally, the file types are shapefile, GeoJSON, KML. I generally also like GeoPackage. I'm getting used to GPKG. GeoPackage files are really great too. So yeah, just a visual representation, but raster is continuous, vector is discrete. Satellite imagery is generally raster data, and you overlay, like Google Maps overlays points, overlays polygons. That's vector data. So just so you see. Okay, now let's get into the climate aspect. So this is a tool called Carbon Mapper. And just to demonstrate what a raster really means with respect to climate mitigation, let's go to, Carbon Mapper. So Carbon Mapper is a data portal to drive greenhouse gas emission reductions by making methane and carbon dioxide data accessible and actionable. So what they have is a dashboard. And on this dashboard, they've identified point sources of emissions. So if I zoom in, you can create this map using Folium, by the way, it's easy. If I zoom in, you can see point locations, and these are generally landfills or oil refineries or gas refining facilities which emit methane and CO2. And if I were to click on one of these, let's click here. This is somewhere in, let's see. So each of these, it's a landfill, Simpson County. Okay, so what you see here, the point is a vector data, right? But this plume is a plume of methane, and they've also calculated the emission rate. They've calculated this for 4 plumes and has used relatively new satellite data called Tanager. And this visualizes the plume on November 9th, 2024. So it's pretty recent. So this gives you an idea of how far these methane plumes are reaching, but also where is it most concentrated. And imagine if you overlay demographic data here or social vulnerability data, you can then find which communities are being most affected within this radius. And then you can have an analysis going to inform policy or reduction strategies and whatnot. So Carbon Mapper is a really cool tool. What I would recommend you to explore is, let's see if I can go back here. Let me just zoom out. It's hard to zoom out here. Find your location, right, on the map, and then see what facilities or what methane emitters exist around you. And this will be a cool place to just gain an idea of what kind of super polluters are near you. And maybe you have some polluters that are not on the map too, so that's a way to contribute to this data. And this is very much open source, free to use, so definitely use Carbon Mapper. Okay, getting back here. So Carbon Mapper is a really great tool to find emission plume data that's open source and easy to just download and use. In terms of vector data, this was an example of raster plumes. In terms of vector data, I wanted to showcase a data set that I helped curate. So this is a global data set of, to my knowledge, if not all, most of the global oil refineries in the world. So all these points are showing you oil refineries that have existed for many, many years. And if I zoom in, so let's zoom into, let's see, which one is this? Toledo. Oh. So if I zoom in, let me switch on satellite view just so you get a better idea. This will showcase an oil refinery here. And if I click on it, it will show me who owns the name of the refinery. So Toledo Refining LLC. Parent owner is Cenovus Energy Inc. Operating company is different. It's Ohio Refining Company. And then it'll tell me the sources from which this ownership data was obtained. So for extracting this data, I used a combination of climate trace and using an AI model called Perplexity has a llama sonar model. So fitting that into the API and then extracting sources and then finding which sources are valid by doing web scraping, essentially. So this allowed me to gather ownership data, which was very much accurate, and you can then cross-verify this data with the sources. So this ultimately was fed into climate trace. So I'll tell you climate trace. This is a wonderful effort that has mapped major industrial assets globally to estimate greenhouse gas emissions. So this is not just methane emitting facilities. It's just any greenhouse gas emitting facilities that are point sources for the most part. So this is a dashboard, climatetrace.org. You can also visit this in your time. And if I zoom in, all of these are sized by the amount of greenhouse gas they pollute. So if I click on here, it'll take me to a shale gas, I think it's a production facility probably, and it tells me the estimate of how many tons of CO2 equivalent over 100 years was emitted in 2023. So 49.93 million tons of CO2 equivalent. That's crazy. So this gives you an estimate of the emissions, and generally it also has ownership data. Not sure if every piece has it, but let's see, metadata. Yeah, not every single piece has ownership, but it's still a really cool tool to find emitters around you. So again, using Carbon Mapper and Climate Trace to help you find super emitters near your vicinity, I'd say that's a good piece of homework to do. And maybe it can inform some local policy or activism or community action. That's the hope, right? So Climate Trace, one more great resource to keep in mind along with Carbon Mapper. Okay, so with that explanation, and again, the reason I showed you this is because these are point sources, vector data points, whereas the plumes are rasters, but I wanted to showcase a climate use case. So with that, let's go into some more details on how do you choose satellite data. What you need to consider first is spatial resolution. This is really critical. Spatial resolution is the size of each pixel in units of distance, and it represents the spatial extent of a pixel. So in this diagram, you see a grid, and each grid is made up, each cell that makes up this grid is 1 meter by 1 meter. So you can see that this is a spatial resolution of 1 meter. That's just the side length of the square of the pixel. And the lower the resolution, the coarser the image. In this case, it's confusing. 1 meter is very high resolution. That means the pixel is just 1 meter by 1 meter, which is a small pixel size compared to most satellite imagery. Low resolution would mean 1 kilometer or 10 kilometers. That's low resolution. And so lower the resolution, the coarser the image. Higher the resolution, in this case, high resolution means the value of the side length of the pixel is 1 meter. It's low compared to 10 kilometers. So just keep that in mind. Low resolution doesn't mean the pixel value, side length is low. So this is just an example of high versus medium versus low spatial resolution, where high resolution, it seems like it's Maxar, Planet, or some kind of commercial satellite imagery. That's high. You can see the cars, you can see the roads clearly, you can see the buildings and rooftops. Medium, which is 30 meters or 10 meters or 30 meters, like Landsat or Sentinel-2, you can't see that many features clearly. It looks like a clump, but you can tell that it's an urban area, and you can see the roads as well. Low, you can barely make out. Like you can see how coarse it is compared to the high spatial resolution. So this is the difference in resolution, and this really matters. It's not always the case that high resolution means great and low means bad. There are different ways to use it on different scales. So let me share another demo of spatial resolution, and this is for land cover. So let's see. What I've loaded here on Google Earth Engine is two land cover data sets. One is a Copernicus-based land cover that's 100 meters in resolution, and then a European Space Agency land cover that's a world cover data set that's 10 meters. So if I zoom in, let's just zoom into one of these fields to show you how resolution really matters. If I click on Copernicus land cover, I'm deselecting it, and I'll open satellite imagery so you can see what's beneath this land cover. So I'm going to unselect ESA land cover, and you can see there's a road in between dividing these fields. Fields on the side, there are some tree patches and probably grassland. And so pink is crops, yellow is grass, green is trees, and red is urban, meaning road or buildings or whatnot. Now, if I click on, this is 10 meter, by the way. This is fairly high resolution land cover. If I click on 100 meters, you can see that all disappears because these pixels are big and they lose granularity. So if you wanted to do, let's say, a city scale analysis or even a farm scale analysis using land cover data, for that scale, you would choose 10 meters because you need granularity. You need to be accurate for such a small scale. Otherwise, everything would be field, or you won't get the roads. But on the other hand, if you're doing it on a statewide level or a countrywide level, you can still use this 10 meter land cover, but then doing analysis or means of land cover in certain polygons, that'd be very, very difficult because the calculations become way too intensive. That's when you use something like 100 meters. So it's manageable, right? So this is just an example of pixel size and resolution differences, and it's really critical to know when to use what and for what reason. So spatial resolution is really important as a concept to keep in mind for selecting satellite data. Next comes temporal resolution, and that's just a measure of frequency or repeat cycle where the sensor returns to the same part of the Earth's surface. So satellites are orbiting the Earth, but they come back to the same point after X days. So the temporal resolution is 3 days, then the object revisits or recaptures that region every 3 days. That's a temporal resolution. But satellites can also be in constellations. Like Sentinel-2 has 2 satellites. Sentinel-1 has 2 satellites. MODIS is split into Terra and Aqua, 2 satellites. So that can reduce revisit time depending on number of satellites because they might have different orbit paths, and then they can, if it's 3 days, they can have it into 1.5 days if they revisit the orbit on one after the other. So this is another tool I wanted to just quickly showcase. It's called Low Earth Orbit Visualization by Leo Labs. And it takes a minute to load, but essentially it's this 3D model of, to my knowledge, most satellites orbiting the planet. Maybe not some confidential ones, but you can even see Starlink on here. You can see MODIS, Terra, Aqua. So if I type in Terra, let's see. There should be, yeah, there you go, right here. So I can zoom into this. This is TerraSAR X. It's moving in the orbit defined for it. It's moving very slow, but you can see the Earth rotating slightly as well. So basically, this is a cool visualization to just find satellites and then see where they are in near real time, really. And one of the best satellite monitoring tools that I've seen online. If you have any more, do feel free to share. So that's how you can determine, and every satellite has spatial resolution, temporal resolution in its metadata, so you can find it on their workbook or algorithm guide. Next comes spectral resolution. This is another very important key thing to determine. So the spectral resolution refers to the number of spectral bands in the sensor, meaning bands are basically set of wavelengths that allow you to determine specific parameters. So in this case, for example, Landsat 8 and 9 have bands, and near infrared allow you to determine vegetation indices. Visible light obviously lets you determine, see the real image, true color image. Band 6, 7 are short wave infrared that can infer burned areas, biomass, soil health, and so forth. And then 10 to 11 is surface temperature, crop water use. So basically, each band has a specific use case, and each band is a set of wavelengths, constrained wavelengths. And multispectral means generally 3 to 10, even 13 bands. But hyperspectral means hundreds or even thousands of bands. And for finding things like mineral signatures and very specific indices for vegetation species, that's when you use hyperspectral, because it has so many wavelengths. It can detect a variety of things which multispectral may not be able to because of the lack of specific wavelengths. And this is just another way to show bands. Instead of saying band 1, band 2, this is the wavelength range for each part of the electromagnetic spectrum: blue light, red, green, red, near infrared, and so forth. Okay, so based on parameters like spatial and temporal resolutions, along with where the satellite goes and how much the coverage is, it's critical to select the right data for the right task. So this is just another example. You can come back to it later. But basically, NASA has pathfinders and specific tutorials for each thematic area. So if you were to select, let's say, atmosphere, you can then go to these subtopics like aerosol backscatter, atmospheric pressure, air quality. Let's go to air quality. I know many people here might be interested. You can then find tutorials on how to use specific NASA air quality datasets. So Tempo is really good for tropospheric emissions monitoring. And then CDAC out of Columbia University has datasets for health and air quality. And you can also, look at these tutorials and find air quality data and tools, so you can really go through NASA servers and databases and find how to use their data. And this is available for not just air quality, but every single one of these major thematic areas, and then you can dive into specific topics. So just wanted to flag that for you. And so what we're going to do next is discuss some very major satellites that are used commonly for conservation purposes, or even vegetation health monitoring, which we'll look into. So Landsat is one of the most long-term data sets that we have. It's the longest continuous record of the Earth's surface as a publicly available data source. The resolution for most bands is 30 meters. The temporal resolution, the revisit time, is 16 days. So you can only have up to one or two snapshots in a month of a region. But the period of record is 1984 to present. So that's a huge and great set of data that you can use for historical analysis. This is a partnership between NASA and USGS, longest continuous record. Cloud cover can be challenging. It doesn't have ways to penetrate through clouds. But temporal resolution can improve if there's multiple Landsats active at the same time. So Landsat has now 9 satellites, out of which not all are active, but let's see, 7, 8, and 9. But other than 5, 4, 3, 2, 1 are no longer active. But if you were to go back in a point of time and then see the intersection between Landsat 5 and 7, or 2, 3, you can find some places where multiple satellites may be active, and that can improve coverage too. NASA MODIS sensor. MODIS is split into is between 2 satellites, Terra and Aqua, and then the spatial resolution varies between 250 to 1,000 meters. The RGB, red, green, blue wavelengths are 250 meters, but there are some bands like the infrared bands that are 1,000 meters. Temporal resolution is really great. It's 1 to 2 days instead of 16 days, and also has a really good historical record from 2000 to present. The resolution is coarser than Landsat, as you can see in this top right corner. NAIP is the aerial imagery program. That's 1 meter. That's fairly high resolution. Sentinel-2 is 10 meters. Landsat is 30 meters. And MODIS, you can see, is just pixelated blocks, 250 meters. But again, if you want to use MODIS for regional or country level analysis, that's great, right? Because it has a daily revisit time and you can get a lot of data because of that temporal resolution. So frequent revisit time makes it useful. Sentinel-2 is a fairly recent satellite. It's only from 2015-16 really to present. Spatial resolution varies between 10 to 20 meters, and temporal is 5 days. Details are that it's launched by the European Space Agency. It's compatible with and similar to Landsat in many ways. Sentinel-2 has 13 bands. And again, it's a part of a twin constellation of Sentinel-2A and 2B. But it's a really great satellite for land cover analysis, NDVI analysis, even monitoring change pre and post disaster, for example. But one quick thing is you only have it since 2015. If you wanted to go back in time, if you wanted to analyze something since 2000 or 1990s, you'd definitely have to use Landsat or MODIS. So just saying that because it may be, advantageous to use this for a lot of applications, but for historical analysis and comparing pre-2016 to post-2016, you might want to use a consistent data set. Now, I want to showcase one example of a vegetation index, NDVI. Many of you may already know. NDVI is simply near infrared minus red divided by the sum of both near infrared plus red. And this is a really great index to measure vegetation health. And it ranges between -1 to 1. The way it works is healthy vegetation reflects more near infrared than red. It absorbs more red wavelengths and then reflects near infrared. So healthy, you can see 50% is reflected, 8% red is reflected, meaning 92% is absorbed. NDVI 0.72, but if it's stressed or just it's fall or it's winter, it doesn't reflect as much NIR, but it reflects much more red, and NDVI becomes lower, close to 0. So +1 or values close to 1 indicate healthy and dense and good vegetation. Values near 0 suggest sparse or bare soil or sometimes just browning vegetation. And below 0 is generally water or non-vegetation surfaces, so you don't really consider that much. But it's used in agriculture, ecological restoration monitoring, and vegetation studies. So let's go into an example. This is using MODIS NDVI. So I'm going to just click on animation link here. And you can see it looks like Africa is breathing. This is a 20-year, let me make sure I'm getting this right. It represents a 20-year median NDVI of Africa for a data set that's a 16-day MODIS NDVI composite. And what you see here is a seasonal variation in NDVI. And I'll send you later a tutorial on how to do this, but you can do this yourself on Google Earth Engine. You can make this for your country or your state or your region. And just have this as a tool to show off as though it's a really cool animation that I personally love. Okay, what I want to show you next is really exciting. It's NDVI improvement. You'll actually see NDVI improving in a restored region. So let's go to climateengine.org. This is a really great tool. I'll talk more about it later. But climateengine.org is one of the best tools that you can use for climate analysis without much coding or no coding almost. I'm going to show you how. So let's this place, let me give a background. This place is called Kanha Shanti Vanam. It's one of my favorite places in the world. It's near Hyderabad, which is a city in India, and an hour away from Hyderabad. And what I'm going to show you is hopefully going to blow your mind. So let me make a map first and go to remote sensing. I'm going to select Sentinel-2 surface reflectance, which just means the true color image. And let's see, it's atmospherically corrected as well. And instead of NDVI, I'm just going to select true color. So you see what's going on before I explain it. So I'm going to select 2017 and, oops, what happened? 2017, let's just pick January or October, whatever the earliest date is. And instead of 2024, I'm going to select 2019, October 1st. Okay, what it's doing now is getting a map layer. And again, I just selected these boxes. It's doing it itself. I'm not coding much. And you can see that it's just make a mental snapshot of this image. You can see that there's some infrastructure here, not that much green cover around this area. It's mostly barren. There are some green patches here and there, but mostly barren and some infrastructure being built. Now, make a mental snapshot of this image and check this out. So I'm going to select let's select another date, 2019, start date, oops. Start date needs to be post 2020 because that's when, it's because the end date is, okay. Let me select the end date first, 2024, whatever, 31st October, and then let's go past 2022. That's when a lot of things were restored. Okay, you made a mental note of that image. Now check this out. Hopefully this loads. There we go. Okay, you can see it's much greener than before. It is a lot of areas have been restored, and this is ecological restoration in real life. This is one of the coolest places you can read about, an initiative called Forests by Heartfulness, and they are a team of experts that restore degraded or barren land, and this is going out throughout many parts of India at the moment. Now, what I'm going to show you next is what's called a graph of NDVI, one variable analysis. So I'm going to just basically drag this marker over here. We can do a polygon as well, but point's fine because the resolution is 10 meters anyways. And what I'm going to do is use Sentinel-2 again, but use NDVI, vegetation index here. And let's go from 2017 to now and get time series. So what is going to happen is it's getting a time series of NDVI on that point across this time period. And this time series will have a 5-day temporal resolution because it's a 5-day data set. So we're waiting because it's processing things. But what will happen is you will see, okay, I'll wait. You'll see an improvement in NDVI because trees are being restored, vegetation is being restored. Instead of being really poor NDVI, now you can see it rising. There's a positive slope here. And this is because of the trees and vegetation that's been restored. So what I'd encourage you is if you have certain places in mind or regions you want to analyze, then do this kind of analysis. You can see images. You can even create NDVI maps here. I'm not going to do that because we are on time. We need to move on. But this is a really cool tool to do this kind of analysis without any coding, right? And then you can download these graphs and just make sure that climateengine.org data is for nonprofit and academic use. So you can make an account here, but it's not for commercial usage or profit. It's for nonprofit only. So I'd recommend using your academic or nonprofit email to create an account and just use it. Use it for analysis. Use it for good. We'll come back to this in a bit, so stay tuned. But this is how NDVI can be analyzed, one way at least, and an easy way to do so. Okay, so geospatial use cases. Just going over the process of how to do this. First, you need to understand the stakeholders' problems and have a deep understanding of what issue needs solving. And this is without geospatial data in the beginning. Just if it's an air quality issue, if it's a tree cover issue, if it's an urban heat island issue, you think about geospatial data later, not in this step. This is the problem understanding step. Then, once you understand the problem and identify who's being affected and what kind of outcomes are desired, Then you go and identify and source and collect the necessary geospatial and ancillary data. If it's a problem of air quality and health, you can collect health data, demographic data, air quality data. Air quality is also split into many different things. You can have PM 2.5, carbon monoxide, ozone, sulfur dioxide. Like there are these so many different kinds of pollutants. So even thinking about that is important. Then you have data pre-processing. If it's not already cleaned and pre-processed, you have to do that work and transform it into a, good clean data set to analyze. This includes handling missing values, outliers, inconsistencies, and so forth. And then you conduct your exploratory data analysis, followed by geospatial modeling, whatever you need to do, spatial regression, clustering, predictive modeling, whatever that's needed. Then you interpret, validate, ask the stakeholders if this outcome is good and usable, and then you deploy and visualize. But many people, even I, we get stuck on, I co-created a model for detecting marine debris, and it's a model that can find where marine debris is located. That's cool. But then working with the stakeholders, working with the companies, decision makers, all that is often left out, especially in academic studies of geospatial data. So I think for making geospatial data actionable and usable, it's really critical to involve all the right stakeholders who can then make the decision and take the data to action. So we'll talk more about that in the near future. Satellite data platforms and tools. So you might have seen this on my first class that I did, but just a review, Google Earth Engine is one of the best cloud-based platforms for processing and analyzing satellite imagery. Provides access to hundreds of satellite data sets and more. NASA also has an Earth data search portal, and you can then, let me just go here. You can also look into earthdata.gov and then create an account and then download any NASA data that you can, because it's free to use by anyone. And then you can have access to Copernicus Open Access Hub. This is the European Union's Copernicus program that allows you to download Sentinel data, European Space Agency satellite data. So it's another tool, the NASA Earth data equivalent for European Space Agency, essentially. And Landsat has its own explorer on USGS, but Landsat's also available on Google Earth Engine. And then you have Sentinel Hub. That's, again, ESA Sentinel missions capabilities. I think now they're trying to consolidate everything into Copernicus Access Hub. So these are all important sources of free, publicly available satellite data. So yeah, Google Earth Engine has two sources. One is, this is the data catalog that Earth Engine, the website of Earth Engine has itself, and you can view all data sets and then find what you need within each theme: surface temp, climate, weather, atmospheric, and so forth. But they also have Sam Roy. He's a really great contributor. Shout out to Sam Roy. He's built a community catalog of data sets that are not yet included on the official website, but you can still use them. So any kind of new papers that have maps like habitat types, population data sets, elevation, land use, land cover, all these data sets are available on Earth Engine through this community SAT.io project. So I recommend checking these out as well, because the data sets on Earth Engine are not the end-all be-all. There's much more to that on the community catalog. And it's a really, really awesome, it's an awesome GE community catalog right here. Okay, NASA Worldview, you've probably seen this before, but just wanted to flag it as one of the key explorers of NASA data. This is one of the best NASA data explorers that you can find, because you can see case studies as well. So for example, bushfires in Australia. If I click there, it'll take me to September 9th, 2019. And let's see if we can see something. You can see some smoke already. Clouds and smoke both, but let's see. Step 1 out of 8. Okay, there are the hotspots. And there we go, on the coast. So you can see these these are likely NASA MODIS or VIIRS hotspots of fires, and it's showing a time lapse. So let's see, 2019 Jan 14, quite a lot of it burnt. You can see these burn scars. So anyways, this is a really great tool to just analyze and find NASA data that's relevant for your Earth observation use case. I'd recommend exploring this much more. And let's see, Copernicus, we went over this. Okay, next section is extreme events and climate hazards. We're going to be talking about how to use Climate Engine for climate use cases, climateengine.org, how to urban heat island analysis, flood analysis. But at this point, let's take a 5-minute break. I need some water. So let's take a 5-minute break before we get into the next section. We'll be back in 5 minutes. I'll keep this on so you can still hear, but I'll be back with some water. So stay tuned, 5 minutes. I'll be back. All right, everyone. I'll be starting back in 1 minute. I'm finally back. Thank you so much for waiting. All right. So, hope everyone's back. Thank you so much for waiting again. And let's continue. So, Now, this section will go over extreme events and climate hazards and analyzing some of those and just showcasing some examples on how to use geospatial data for event identification and assessment. So in terms of climate adaptation, you can use satellite data for extreme event detection, so identifying and tracking extreme events like hurricanes, typhoons, storms. That's more in the meteorological department as well. Then you can use it for damage assessment. So you can use it to assess building damage, landslides, wildfire damage like burn scars that you saw. There's also a use case for response coordination. So if you're interested in near real-time satellite data, it can aid to some degree the coordination of emergency response and disaster relief conditions. You can also use satellite data for creating early warning systems for advance notice of extreme weather events. Again, meteorological departments do this all the time. You can also use it for modeling and forecasting, short-term and long-term. Predicting extreme events in the near term is more weather-oriented, but then you can use it for climate modeling. So seeing what scenarios exist in the next few decades based on climate models and temperature and so forth. And again, you can use it for trend analysis for long-term satellite trends, and finally integrate data with in situ, on-the-ground data sources. And this will provide a much more comprehensive understanding of extreme events. If you just look at wildfire scars or just look at heat waves from a satellite perspective, you may lose out on the ground-based perspective from sensor data or from even human-collected data. So I think one of the most powerful combinations is combining geospatial satellite data with location geospatial sensor data or collected data on the ground in situ. Okay, let's get back to Climate Engine. I have one more or a couple more things to show you on Climate Engine. Let's just open, let me see. Reload this. Okay. So what I'm going to show you here is essentially, you probably heard of Hurricane Helene, which happened which struck North Carolina fairly hard in September. And what we're gonna do now is get a time series again, but let's go to Asheville, North Carolina. Asheville was hit hard by Helene, and what we're gonna do is use CHIRPS. CHIRPS is a great daily data set of precipitation. And what we'll do is go create a time series from August 1st to end of October and get time series. So let's see. You can see this unimaginably high precipitation compared to the rest of the last 2 months, right? And this is insane because this is when Helene was hitting on 25th, peaked on 26th, and down on 27th. But this was the 3-day damage that to this date Asheville is still recovering from. And we can see here that on September 26th, Asheville Citizen chimed, like many other news articles, but this is an example. That's when the hurricane hit, and that's when precip peaked. And so my point is, using such analyses, you can obviously go back historically and see what happened and then figure out trends based on extreme events. Another quick example is, let's go to, let's see, Airfile Land is decent, or GridMet. Why don't we use GridMet? GridMet is a continental US-based data set that is 4 kilometers and also has many variables like temperature, precip, humidity, and wind speed, and so forth, even ET. So if we go to maximum temperature, what I'm going to choose is, 801, this is fine. Los Angeles, because LA had a massive heat wave that was much worse than what it faced ever, almost. So I put LA as the point. Let's go to the map and make sure we are on LA, one of my favorite cities. And let's go to figure data. Okay, let's run this time series. So what it's going to do now is create a time series of maximum temperature um, between August and October. And you can see on September 6th, it was hovering around and exceeded 40 degrees Celsius. The max temperature exceeded 40 degrees Celsius, which is nuts. And I pulled up this heatwave climate.gov article, and you can see that this snapshot is from September 6th, where daytime high temperatures exceeded 100 degrees or more in much of Southern California, including LA, Nevada, many parts of Western Arizona too. So just to show you, you can create these kind of raster maps on Climate Engine as well. You can make let's see, you can actually make a map and do the same thing that I did. It's going to create a mean of that though. But you can, the more useful thing is seeing, in this case, when this temperature was peaking and what days were surrounding it. So anyways, this is a way to identify heat waves. This is a way to identify extreme events. You can do this for many variables, not just temperature and precip. You can look at available data sets here and then select the variables that you want to map or plot. And this is, again, super useful tool for doing trend analysis and then getting such data, even for academic studies and research or policy info. So that's one way to use Climate Engine out of many others, but I showed you use cases for vegetation health monitoring and temperature and precipitation analysis. Let's go to this application. I know many of you mentioned that you are really interested in analyzing urban heat islands in cities, and I want to show you at least one really good example of an application that was created by TC Chakraborty and Lee, and they have a paper out on it. So let's open that map. And what they've done essentially is this application displays surface urban heat islands in 9,500 cities around the world, close to 10,000 now, I think. And they've used data between 2003 and 2020. So I'm going to do some top-down explanation, meaning I'll show you the application first and then explain how it's working. So if we zoom in, we can see urban clusters, and these are cities, major cities in the US, which have the urban heat island data. So if I zoom into, let's see, what is this? Where are we? Okay, we're near Dallas. Okay, awesome. So Dallas, if I click on Dallas, what it'll do is calculate the annual daytime, meaning it's the mean annual daytime surface urban heat island intensity. And what this means is it's the subtraction, it's the difference between land surface temperature in the urban pixels minus the non-urban pixels. Annual nighttime is lower, obviously, because we're cooling in the night, but it's still 0.5 degrees warmer. And urban heat island effect, I'm sure many of you know, is this heat island effect warming in cities because of concrete and dark structures and darker roads, asphalt, and lack of green cover, which creates urban heat compared to rural areas, which might be greener. So there's a difference in temperature between urban pixels and non-urban pixels. And this urban heat island intensity is that difference of the mean land. It's based on land surface temperature. So what we're using here is a MODIS 1 kilometer resolution land surface temperature dataset that divides itself into daytime and nighttime. And this graph is essentially showing us the annual daytime SUHI, or surface urban heat island intensity, between 2003 and 2020. So you can see that there's a trend here. It's not too much of a trend, but it is, the minimum has increased, and now it's warmer than it was in 2003. So you can see this trend for nighttime. It's slightly less. It's interesting. So what this is doing is, over this urban extent polygon, it's calculating the means and then getting these numbers for the whole polygon, not the individual pixels. But that being said, you can see these land surface temperature pixels. Each one of these are 1 kilometer pixels. And if you overlay, this is an idea for everyone watching, if you overlay tree cover and you overlay demographic data, then you can find one, where is tree cover lacking, which needs more tree cover, right? And you'll often most likely find that the hotter areas, which are more orange and red, lack tree cover. But you can also then overlay it with demographic data. So finding out which socially vulnerable populations are in extreme land surface temperature, extreme urban heat island areas, and where can trees be prioritized based on social vulnerability. So this is an example of how to use this, and this is a really, really great tool for just finding urban heat island across, not just in the US, but you can find this, because MODIS is a global data set, you can find this in many cities. Let's see if India has, yeah, India, there we go. Let's go to Mumbai. Yep. Interesting. Yep. Okay. Anyways, I don't think this Mumbai data set, it needs some work. Yeah, it's definitely changed a lot in the past 5 years, so this is still outdated. It's 2025 almost now. But anyways, it's still a very useful tool, and you can then update this with your own data sets as well and add things like tree cover, land cover, population data, and so forth. So this is how it works. MODIS has a 1 kilometer LST dataset on both Terra and Aqua. So there's MODIS Terra's LST and MODIS Aqua's LST. And it's a really critical dataset for environmental monitoring for urban heat islands and heat monitoring. So this is just a plot showing you Terra and Aqua nighttime, daytime, and then a machine learning model finishing the pixels or filling in the gaps. The calculation method is, like I mentioned, the UHI intensity is mean LST of urban pixels minus mean LST of non-urban pixels within the urban extent polygon. The mean LST that you just saw is computed for all urban and non-urban pixels within that extent. I'll send you the paper via email, but the algorithm is basically using MODIS LST data from Terra and Aqua at 1 kilometer. Nighttime and daytime are considered separately. As you saw, there's nighttime and daytime plots, but the algorithm only selects clear sky pixels with an average LST of less than 3 Kelvin, because more than that would basically screw things up and not be that accurate. So this is a really great tool, and there's a paper on the methodology if you want to check it out. Just look up Global Surface UHI Explorer and you'll see it. And I'll send all these links later too. I'll mention how to access those. Next up is this, let's see, it's a flooding. I know many people were interested in flooding and city flooding. So there's this app. Let me make sure I still have it because I might need to find it. 1 second. Here. It might be actually be on my terminal. There we go. So there's another, I'll tell you more about what I'm doing here, but essentially there's an library called GEEAD, and you can get the source code of many applications using that. So you can learn how this was coded, build on top of it. If it's a publicly available app, you can easily do that. But I wanted to basically show you how to do this. So this is an app called View Flood 2021 Vancouver. Funnily enough, I was born in Vancouver, so this is an interesting application here. But what this is doing is using flooded pixels. Let me mute that for a second. There's Sentinel-1 and Sentinel-2. So Sentinel-2 showcases imagery, the 10-meter imagery that we talked about, invisible true color RGB. I think there's some false color compositing going on here, but it's just RGB imagery in some combination and showcasing that. So let me zoom into this area. Let's see. Yeah, these things take a minute to load, so you always have to be some patient with them. So SAR, synthetic aperture radar, and what we're seeing here, look at this. You can clearly see that these areas are darker and likely filled with water, and so there's flooding that happened. before here, it's clean. I mean, it's not flooded. It's green, and you can see the vegetation. Whereas here it's darker, and you can see that the river has flooded many parts here. So let me switch off Sentinel-2 and then look at this image. This is called synthetic aperture radar Sentinel-1 image. And Sentinel-1 is a microwave-based satellite. It's not using the same wavelengths as the Sentinel-2 is. Sentinel-1 SAR has its own set of bands. Oops. Yeah. Okay. Own set of bands. And we're seeing the C-band image, which is, I think, 4 to 10 centimeters, if I'm not mistaken. And so the coolest ability that SAR has, okay, check this out. Why is this not working? Okay. Okay, something's up. Yeah, there we go. Okay, so I'm going to use these instead of using my cursor. That's the problem here. Let me switch on Sentinel-2 to showcase what is cool about SAR. So this should load in a minute. Make a mental note of this side. So you can see on Sentinel-2 there are so many clouds. Probably because it was raining and flooded and you know what. But Sentinel-2 is RGB. These wavelengths cannot penetrate clouds. They're blocked by clouds, right? So you need cloud masking and whatnot. But Sentinel-1 doesn't care. It is able to penetrate through clouds because it's a longer microwave wavelength. So Sentinel-1 SAR imagery doesn't care about clouds. You can go through clouds and penetrate clouds and then see the flood extents very clearly. So Sentinel-1 is often used for flood monitoring, even earthquake monitoring, and certain types of deforestation analysis in tropics because it doesn't, care. Clouds don't matter for it. And the way this is being analyzed, and I'll explain more in my slides too, there's something called backscatter, meaning if you let's imagine you're shining a light beam on a wall. Some of that light, not all, but some, is being reflected back at you. Similarly, when SAR satellites or Sentinel-1 satellites, most satellites will have backscatter, but that's lost in the atmosphere. But SAR is microwave, so it's a longer wavelength. It's not covered or blocked by clouds or much of the atmosphere either. So what happens is there's a difference in backscatter between vegetated areas and flooded areas. So you can see that flooded pixels let's mute flooded for a second. Flooded pixels are basically highlighting all the water extents that weren't there in the previous image, right here. And here's how it works. So SAR has separate pixel sizes for each band. It's a bit confusing. You can look it up. But each band has a polarization, and then there are separate spatial resolutions for each. The temporal resolution is 12 days per satellite, but Sentinel-1 is split into Sentinel-1A and B, so 6 days together. And the period of record is 2016 to now. It is a radar-based satellite. It penetrates through cloud cover, making it one of the biggest advantages over visible imagery. And it has twin satellites. So the way it works is that calm water surfaces scatter SAR radiation away, resulting in low backscatter and a higher contrast with land. So you can see here, like even visually, you can see which areas are flooded and which aren't due to this comparison. But the SAR backscatter really, in this flooding algorithm, maximizes that contrast. So low backscatter identifies flooded areas where land is typically observed. And I don't have time to get too much into detail, but there is a NASA RSET tutorial on just SAR, right? They have two polarization, VV and VH, and that's used to detect flooded vegetation effectively. You can also, for flood analysis, use digital elevation models that can tell you where runoff is happening, where inundation is being hit, and basically Sentinel-1's data with DEM data can provide very powerful insights into flooding and how water is flowing in these flood zones when at the time it's happening. So again, I'll send you the link. This is a really great app to just learn, and there's code behind it that's open as well. So I'll send you all of that and tell you at the end how to do that. Okay, moving on from flood and urban heat islands, there's drought. So droughts are really tough to really define and map because there's so many ways of identifying drought. There's hydrological drought, there's agriculture drought, there's short-term drought, long-term drought. So there's a variety of methods that can be used for identification of drought. But what I wanted to show you is there are many data sets or tools that you can use for drought monitoring. Now, if you're based in the US, there's a drought monitor by US Drought Monitor that tells you every month which areas are at risk of drought. So it seems like parts of some northern states and let's see, interesting. Yeah. So it tells you a map of which areas are high at risk. And this is essentially, I think this is based on SPEI or SPI. I'm not 100% sure. Let's see. Data about, let's see. So it's basically using classifications on how dry areas are: abnormally dry, moderate, severe, extreme, or exceptional. Red is extreme, and it's concerning to see that there's some areas here that are in red, dark red, meaning water really needs to be conserved there, somewhere in Texas. And it gives you an idea. But essentially, there are several indices, such as the Standardized Precipitation Index, SPI, which just analyzes the precipitation deficit. How much has it historically precipitated? How much rainfall and other things have happened compared to now? And it's a deficit in precipitation. But then there's SPEI, separate one, that's called Standardized Precipitation Evapotranspiration Index. So that considers both precipitation and evapotranspiration by vegetation to determine drought conditions. And there's a very complicated formula for that. You can read about SPI and SPEI. Then there's soil moisture deficit and runoff indices. So these are separate for different kinds of drought. Soil moisture deficit is often used for ag droughts. So if you want to just analyze drought for farmlands and agricultural areas, that's where you use that. And then runoff indices are useful for urban or near urban droughts. And so there's Global Drought Monitor, which is a global data set by Copernicus and European Union that is loading. Let's see. Okay, yeah. This shows you a very coarse, low resolution drought map globally, and you can see that the methodology differs between this one and the UNL US Drought Gov. You see that the map is different. And that's why part of why I said drought mapping is really difficult, because there's so many methods to do it and not one that's universally agreed upon. But they're agreed upon for specific drought types, but it might vary region to region as well. There is, if you're based in Europe, there's European Drought Monitor that's specific to Europe, and it's a mini subset of the Global Drought Observatory. The global shows you the whole thing. Europe shows you just the European part of it. I'll just, it's a combined drought indicator. It's only for Europe, but these things have separate methodologies to the global one. You can see this is separate. You can see the European part. It's not the same as this map. So you have to read the specific methodology that each region is using. So there's US, global, European, and then finally India has its own drought monitor that I could find. I'm sure Australia might also, and some other countries. But and again, this is more local to the region itself, and the methodologies might vary by country. So just make sure that whatever you use, make sure you know the methodology of that region. And and find out if it's appropriate. So moving on, we did see hazards on worldview, but I want you to see what's happening right now. So this is in Malibu in California. As of December 10 and 11, there were fires in Malibu, and these were fanned by high Santa Ana winds to the Pacific Ocean. So you can see smoke going out from these fires. Now I can zoom in, and even you can rotate it because it's a 3D visualization, and you can basically zoom in, see how this smoke was moving, and this is a part of NASA Eyes, which has it for specific events around the world. So this is, let's see, November 26th, nighttime glow of Icelandic volcano. That's pretty cool. So anyways, this is a way to visualize certain events, and maybe you can think about creating such things on 2D using Google Earth Engine, or 3D if you have access to Google Earth, and then you can import these files. So anyways, just another way to visualize events. Just an exciting piece here. Okay, so you know about NASA Worldview, NASA Earth Data. Let's move forward with environmental degradation. So this is a place where I want to showcase certain deforestation things. So let's start first with Global Forest Watch. This is one of my favorite things to show. Even in videos, I've included it for mapping indigenous landscapes. So let's check it out. Let me see. Okay. Why is this not closing? Okay, one sec. Okay, I'm gonna go to Brazil for this demo. Let's see, Brazil is here. Okay, now check this out. I'll just zoom into Brazil. And what? That's weird. I literally did this yesterday and this was working. Okay, there we go. All right, so I'm in Brazil, and then I'm gonna click on tree loss. Let's click on tree loss. Okay, protected areas. Switching those on indigenous and community lands by landmark. That's another data set. Switching those on, and then why is what I wanted to showcase is the intersection between tree cover loss and indigenous and community protected lands, and it's a very, very stark contrast that would be really great to show. Let me see. Okay. Yes, there we go. Okay, so what I have on this map is showing you tree cover loss, right? And here's another piece of interest. I'm gonna zoom into a state of Brazil called Rondônia, and do a time lapse from 2001 to 2023, so you can see how this progressed. Now notice the blocks in brown that are indigenous and community lands. These are protected areas for indigenous communities and acknowledged by the government officially. If I switch those off, you can see clearly that that's where deforestation has been the slowest or most minimum. But around those areas, around these indigenous landscapes and community managed lands, that's where you can see tree cover loss being the maximum. Again, I'm going to just show you, switch it off, and then back on. Not to say that it's not happened in indigenous lands. Of course, there are some areas, but compared to the rest of the non-indigenous landscapes and urban areas, and even areas not protected or recognized, that's where deforestation has occurred for the most part. So the point I wanted to showcase here is just that protection of indigenous rights is so important for conservation, especially in the tropics, where land is being lost at a very high rate due to agriculture and palm oil plantations and fires and so forth. And just to, again, one more time, this is not just a story in Brazil. Even if I go to, let's say, another country up top, Colombia as an example, or Central American countries, it doesn't matter. You'll see the same kind of trend where indigenous acknowledged lands are facing lower rates of deforestation, significantly lower than non-indigenous ones. And so human rights, in this case indigenous rights, go quite hand in hand with conservation, especially in tropical forests. And that's not to say that all indigenous cultures are very different from each other, and we can't generalize things, but where indigenous cultures are following ancestral practices and respecting land and holding nature sacred, that's where we can see that land is protected. So just want to shout that out. And if you ever get a chance to advocate for indigenous rights, for biodiversity conservation, make sure to just link those two things together. Or you can showcase this map and as a demo for the people that you want to communicate to. Okay, that's one app. Then comes this deforestation app. That's by the University of Maryland. This is primarily a good tool to just showcase when deforestation happened and where it happened. So this legend here tells you this is separated by year. So let me go here. If I were to switch on satellite view and then click this off, essentially you can see these farms now that weren't farms before. This is part of this is part of the Amazon essentially. And let's see, it's not yet, I guess it's not updated either because it's only up till, let's see, 2020. Okay, yeah, fine. So you can see these lands, and not every land has been classified yet. Maybe there are some updates that's needed, but many farms are included here, and maybe the old ones are most included because these are from, seems like 2000 from this legend. So this is a map just to showcase if you wanted to find out in your region when some things have been deforested. If it's more recent, that just means that more land around it is going to probably be cleared. Like this is 2023, just last year. And that means probably these areas are going to be deforested soon. So it can be a trend identification mechanism for you. And if you wanted to see in your region what's being deforested, this is a good place to look into instead of the Global Forest Watch. So I'll share all of these links with you, so don't worry about that. Yeah, you saw the Global Forest Watch. Mind mapping, so this is one thing that I'm involved in, and essentially, let me go here. Along with refineries, I'm building a global data set of mines, and it doesn't have, well, some of it has ownership yet. Everything remains, but let me go to Senegal mines because it's a more well-defined demo here. You can see, let's go to Senegal, and here you can see some of these points that are defined mines, and we also have a polygon on top of it, meaning you can see what the mine name is, mine owner, operator, country, and essentially what we're doing is creating buffers around them. And if I were to overlay something like, let's see, protected areas, you can see that which mines owned by who are within what proximity of protected areas. So this is a protected area in green, and if I were to zoom down, this is quite illegal actually. This shouldn't be the case, but this is a mine owned by Massawa mine, 90% owned by Endeavour and 10% by the government of Senegal. And it's actually not even intersecting partly, it's within a protected region. And if I were to click on, let's see, click on this protected area, that's, I need to name it, but yeah, that is, let's see. Okay, it's still, let's see if it has a name. Park National Federal. I guess it's called Park National do Niokolo-Koba. So that's an actual park, and that's protected region, which this mine is in. So this kind of analysis allows me to see what mines are where, owned by whom, and then within what protected region. And you can do this for anything, not just mines. You can do this for refineries. You can do this for landfills. And instead of protected areas, you can use vulnerable communities, population density, ethnicities, like whatever you want. This is just one example of using one vector data with the other and then finding intersections. And so in the end, what you can get is an exported file showing what mines are owned by whom within what protected area. And then those can be penalized if you have contacts with policymakers or banks or whatnot. So this is a way to, again, thinking about that initial thought where you want to link these kinds of data use cases with action. And that's the whole point of this webinar, and whatever I'm doing is trying to link data to action. The other last piece I wanted to show you was a global palm oil dataset, coming back to the palm oil example at the beginning. This is from 2019, so it's still 5 years outdated, but it's an essential dataset that showcases where palm oil plantations are in the world. And maybe not 100% coverage, but there's still, let's see. You can see these are palm oil plantations, not forests, palm oil plantations. One species, uniform rows, cut like rectangles, and this is what's replacing a lot of tropical and forests in the world, especially tropical ones. So this is highly devastating because, I mean, it just kills a lot of biodiversity in tropics. So this is a data set that identifies which areas of the world have palm oil plantations. And one good thing is that palm oil has the highest yield per hectare. So it's still useful because it uses less land. But the problem is that it's replacing tropical rainforests instead of being grown on degraded lands or elsewhere that's suitable. It's replacing actual tropics. They're being cut down, and then this kind of monotonous plantation is replacing that. So this is a part where you have a data set that identifies where it is, and we need to do some creative storytelling or data visualization, or basically link it to an action which minimizes the impacts or at least minimizes the creation of more plantations. And that's the key challenge. It's easy to detect features. It's easy to make these maps. It's harder to actually translate to action. So just keep that in mind. Think about ways that you can use data in your life, in your region, and then translate it to impact, whether that's working with a company on the ground, nonprofit on the ground, policymakers, students who can then do something about it. Those are the kinds of things that I really would love for you to think about. If it's the urban heat island explorer, then the question we should be asking is, we know that this is hot. We know these cities' spots are hot. We know that they lack tree cover. What areas can be prioritized for funding tree cover planting based on the data that we see? That's the kind of questioning and kind of thinking that climate action needs from us geospatial folks. So yeah, that was just a quick another example. And yeah, I can't be tired of reiterating that geospatial data can inform decisions, but data is only useful if it can be translated to action on the ground. Data itself isn't a solution, but a means to implement the solutions effectively. So I just really want to hammer this in. I feel like there are so many companies, even the one, some of them I've worked for previously, that think data means we're solving the world's problems, but that's not true. You're only providing data that can inform decisions, but if those decisions or actions are not implemented, then it doesn't mean much. It really doesn't. It's like having a good idea. It's only useful if it's executed. Data is only useful if it's translated to action. So with that being said, there are many sources of data, geospatial data. We saw many satellite imagery data sets. There's aerial photography, aerial photographs usually captured by aircrafts. A lot of the carbon mapper stuff that I showed originally at the beginning, they are aircraft derived with methane sensors, having spectrometers detecting methane. So that's an example of aerial photography. And then there's a national aerial imagery program, and maybe your country has a imagery program too. There's LiDAR data. We didn't talk much about that, maybe in a future session, but LiDAR is a remote sensing tech that generates very precise and 3D representations of the Earth's surface and vegetation. It's used very commonly in archaeology and even deforestation monitoring, forest carbon monitoring, because it's so precise. It's laser scanned, and it's a really cool 3D tech for representing vegetation and surfaces. There's point data from open sources like OpenStreetMap. OpenStreetMap has crowdsourced geographic data. So unlike Google Maps that's closed and owned by Google, OpenStreetMap is the open version of it, but it is crowdsourced, meaning they may not have accurate data all the time, but I still think it's one of the coolest data sets, especially for roads and buildings and spatial features. Census data, socioeconomic data, that all is separate too. So this is the kind of, if you're wanting to become, or if you are a geospatial data scientist and want to improve, or just want to find out more opportunities, I'd recommend learning. I mean, you probably already know data analysis, spatial analysis. Machine learning is great to have as a toolkit, especially for complicated problems that may need a lot of human hours, but can be faster in machines. And I think that one of the most important things for geospatial data scientists that's not emphasized often is communication. Strong written and verbal communication, but also good storytelling. Data scientists need to be storytellers. We understand the data better than most people will because we worked on data. But if we cannot communicate these findings and collaborate with interdisciplinary teams and translate technical concepts to non-technical folks, then no matter how good the data is, if the communication is poor, the implementation will be poor. So I think data scientists need to be good storytellers. I find that quite valuable. And then tools of the trade, you already know this, but there's ArcGIS and QGIS as softwares to analyze things, but I generally do most of my analysis now using Python. Several people, my peers who are ecologists, use R. It's another programming language that's really great too. No shade thrown. I have nothing against R. I prefer Python just because it seems easier, and I've practiced in Python for many years. SQL is good to know because SQL is used by geospatial folks and GIS scientists to interact with large spatial databases. Examples would be PostGIS or BigQuery that have huge amounts of data. So SQL can help you find things quite easily in that, instead of using something like Pandas, which cannot open like a 250 gigabytes file. It's not doable. Then there's cloud-based platforms. So Google Earth Engine, AWS has access. Google Cloud has dataset access. So just learning at least one cloud-based platform, well, whether it's Google Cloud or AWS, it might be useful for you too. This I'm not going to go over much, but obviously there's a Python ecosystem of libraries for geospatial analysis. This is just for you to just know. I won't say each one of these, but if you want more resources, I can send you those as well. And again, visualization is its own beast. I personally like Mapbox, Leaflet. There's Leaf Map by Qiusheng Wu. Dr. Qiusheng Wu is amazing if you don't follow him already. So these are some tools for viz in GIS. And of course, data integration, data quality assurance, scalability, spatial complexity, all these are things we need to worry about and think about. And then ultimately designing really good visuals for good storytelling. That's another skill itself. So I think once we become effective data scientists, I'd say it's equally, if not more important, to communicate that story well. So that includes good visualization, good storytelling, good communication and translation of the findings. And so I'll end here so you have a lot of time for questions. If you haven't subscribed to the channel already, please do subscribe. It helps out quite a bit. if you want a PDF of curated resources, including some of the things I mentioned, as extra resources for learning, do DM me on Instagram. You can follow me at PlanetSapling, easy to remember. And if you are personally interested to participate in a global data scientist network for climate action, I'm actually creating and managing a global community of nearly 200 people now, all over the world, up from 60 countries, to focus on specific themes within climate action using geospatial data. And the channels are organized by theme, but then you can also connect with fellow country people. So if you're interested, it's a Slack community. Again, just DM me on Instagram and follow me there. You'll get access. And finally, if you want access to more code, more resources, just a lot more instead of just freely available things that I do, you can follow me on Patreon. That's where you can find me as PlanetSapling, but I'll send you this link on the chat too. That's where I'll send Patreon members applications, Google Earth Engine applications that I've curated, specific code to access certain things. It's a lot more comprehensive. It starts at $6 a month. You can also join for free initially and then make up your mind. But Patreon really helps me out because it allows me to keep continuing doing this. This kind of webinar building takes a lot of time and effort, and I can do more if there's some more funding, honestly. So I'll send you this link on YouTube. Let me find the YouTube. But yeah, if you're now, the table is open for questions. So if you have any questions or concerns or things you want to ask, I'm going to monitor things and just make sure that I'm, let me see. There we go. Okay, live chat, open panel. Okay. Oops. This is not my this is not my own channel, but I've sent you the link on the chat. So I'm open for questions. Yeah, feel free to ask questions. Okay, can we overlay hazard data with asset data on Google Earth Engine? Absolutely. You can, if you have a layer that is a hazard layer, for example, extreme heat or the urban heat island effect data sets or the flood data sets, you can overlay it with vector data. So you can load in a shapefile or CSV, and then overlay the hazard layer. So yeah, raster and vector data, you can definitely combine them on on the Google Earth Engine. Let's see. Yeah, feel free to ask questions. This is the time to jump in, see whatever you want. Can I integrate some data API to my project free? Do you have your own API, or what API are you asking about? Thank you. Really appreciate the kind words. Okay, Leonardo, I see your question. Working with economists, do you collab? I don't work with economists yet, but I hope to, because I'm hoping to gather more stakeholders within the global community I mentioned, and that'll help with connect climate hazards with economists. So I don't yet, but I plan to. And do you see economists working with satellite data? I don't. It's not common. But what I see is based on climate hazards on based on a regional climate hazard analysis, economists can come in and analyze the economic cost of not acting. So they can do economic analysis based on climate hazards from geospatial data. So that's something I can see, and even climate models. So I do see um, climate models producing different hazard layers based on the emission scenarios, and then economists trying to quantify the damage to the economy based on climate change. That's happening for sure. Earth engine in Ethiopia. Oh, I actually don't know if it's accessible there. It should be, but I can check. I can check and get back on that. I don't know. Any other questions, comments? Have you used any of these sites to analyze data from the Caribbean islands? I want to know up to date. I haven't yet. I'll say that climateengine.org should have data that you can use for Caribbean islands for sure. Um, and I'd say that would be fairly accurate. But I can look for specific data sources. I haven't personally done anything in the Caribbean, so I'm not 100% sure. But you can definitely use Climate Engine for Caribbean for sure. Yeah, opportunities for satellite data to fill data gaps in CSRD and ESG. I think a big gap in scope 3 emissions might be a little difficult, but at least um, validating the emissions data for point sources um, in companies, so things like factories and mapping supply chains. That's where satellite data can shine and fill in the gaps in ESG reporting, because ESG reporting relies a lot on self-reported data at the moment. But I think satellite data can really fill in the gaps to validate whether the self-reporting data is accurate. So if there's mining companies and they're saying we committed to zero deforestation in 2025, well, we can actually see that and using satellite data and measure that. So that's something we can fill gaps with. How to get LULC data for free from 1980 to 2024. Um, it depends on where you're looking at. There are certain land cover data sets that go back to 1980, but 1984, not 1980, and that would have to be Landsat-based land cover maps. So it depends on where you're looking. One, if you're looking for North America, North America has its own NALCD, North American land cover data set, and they do that every 5 years. I think since 2000, if I'm not mistaken. So it really depends on where you want the LULC data. Any more questions? I'll be on for maybe 10 more minutes. So if you have any other questions, feel free to ask. Yeah, great question. How do you handle spatial data quality issues like missing values? Um, so it depends on how it's happening. If it is just few pixels here and there, what I'll do is use spatial interpolation, whereby it is looking at nearest neighborhood pixels and then finding out the mean or median depending on what data set it is, and then interpolating using that statistic. But if it's a lot, like if it's big gaps, missing values that are huge gaps, in that case, I would do my best to find historical data for those gaps and then find mean within that historical data, um, or just mask it if it's too big and there's no other data available. because it's not good to just guess data for large gaps, because it could lead to inaccurate reporting. But but yeah, if there are just a few pixels here and there, I'd do spatial interpolation for finding the values or estimating them. North Africa. I I okay, North Africa. Let's see. Let's just actively look together. Um, Africa land use, land cover, Landsat. So, um, I guess this is one for Nigeria from 2020. And yeah, okay, so this is from 2016 to 2020. That's good. 1980. Um, let's see if there's anything from 1984. Um, yes, I'm on LinkedIn. You can find me on LinkedIn as Ankur S. I can find my link too. But uh, let's see. Yeah, I'm not sure. We'll have to do some digging, Mariam. But I can get back on what's available for North Africa since that time, because there might be global land cover data sets that have been created in studies, which you can find, but I'm not sure if there's a North African specific one. Um, okay, thank you. Specialize in network methods, graph ML. I'm interested in combining with geospatial data science. That's really cool. Good tools and projects. I can find out good tools and projects that combine graph ML. I'm not super familiar with network and graph ML myself, but I know some friends who are, so I can get back on that, Didi. And if you registered, I still have your email, so I can email you back. Do you see the skills displayed here as enablers of a lucrative small business in the short term? Micro enterprise? Yeah, I think so, because you can find contracts with other companies needing geospatial data and charge them for your services. So that's kind of how PlanetSapling is working right now. I'm charging companies or nonprofits based on the services I offer, and you can totally do that too. You can find good contracts and then charge based on the deliverables. Um, so it can work, but you need good connections or industry connections to find such opportunities. Um, Collaborate with universities or high. Well, I am so I am collaborating with a nonprofit that's an academic institute called Desert Research Institute. I don't collaborate with enough universities, and I'd love to, because what I'm trying to do is build this global network of students as well and people in universities. And you're right, it would promote capacity building and knowledge transfer. So I would love to, if you have ideas, first of all, I'd love to chat more. But yeah, that's something I'm aiming to do in 2025 later on too. Best free satellite data options for crop monitoring, small field sizes. In the U.S. there's a agriculture data set by National Aerial Imagery Program, and that is 1 meter resolution, and that's excellent for ag monitoring. In some cases, like I know a company in India doing drone monitoring of fields, small fields, so they're using their drone data sets for analyzing things like NDVI or tree cover and so forth. So it really depends on region one. Second, if you just need NDVI or just need RGB monitoring, I'd recommend, if Planet is available through your institution or in collaboration with your university, then Planet Imagery might be a good bet, because it's near 3 meter resolution and it's pretty high resolution for farm monitoring. So yeah, I'd recommend if finding an opportunity to get free Planet data with your university or company or nonprofit. Also, I'm not a PhD, so I'm not a doctor for people thinking and calling me doctor. um, Oops. Okay. Any other questions, comments? It's getting close to time, but I'm still happy to stay on if people need to chat. And you probably, if you registered, you have my email. It's just ankur@planetsapling.com. Feel free to email me for any specific questions if you have some. But yeah, I'm happy to share again. And if you can follow me, subscribe to the YouTube channel, and just share this work, I'd really appreciate it. And if you want more access to exclusive code and resources and more things, applications too, feel free to join my Patreon, which should be in the chat. So yep. Um, Thank you so much again for attending and spending a Saturday morning with me. It might be evening for you, so thank you so much again. And I'll take leave. I really appreciate your time. Definitely. I don't know what your name is, LA. I'd love to connect. And yeah, feel free to connect with me on LinkedIn or email me. Silky, I just see your question. If I remember correctly from your presentation, yeah, Climate Trace and Carbon Mapper are great. I would say Climate Trace is better because it has more asset coverage. So if you want to find asset data for companies, especially in the manufacturing, mining, oil sector, it's really good. Even cement to some extent and chemical factories. So I'd say use Climate Trace more. But if you want extensive plumes and emissions, then Carbon Mapper is good in combination with Climate Trace. Thank you, Joey. Thank you, everyone. Really appreciate your time. All right, I'll stop streaming and feel